My calc babies, you are in chapter 3, 3.1, and the topic of this first section is the idea of relative extrema. Okay, so look, the way I think about this, the way I need to be able to proceed in mathematics is, as I've said, I either need to see an application or I need to see the geometry, but either way, I'm simply asking the question, what does this do for me? Okay, like in other words, what value, what utility is this lesson going to give me? And a lot of that is going to be determined by, or if you know the types of questions that you're going to be asked, right? So let me go ahead and give you like just a brief summary of what chapter 3, the types of questions that we're going to be asking in chapter 3. Now, one of the questions might be, and I'm going to erase and do this quickly, so if you don't mind, put your pens down for just a second. Let me just go through the types of questions that we're going to ask, right? So if I have some random function here, and I'll draw one more. So I have two random functions drawn. So I might, or I am, one of the things that I'm going to be asking in this chapter about this function is, hey, does this function have a minimum value or a maximum value, right? I mean, if you think about it, we ask questions about minimums and maximums all the time. I mean, think about if you, I don't know, if you, I have no idea what the inside of a gym looks like, but if you frequent a gym, you might ask your buddy, dude, what's the max you can bench press, right? What's the max you can squat, right? We're always, or what's the maximum speed that car will go 0 to 60. We are always asking questions about maximums and minimums. What's the minimum cost that I can get away with, or the minimum? What's the minimum amount of time I have to speak to this individual I don't necessarily like? Do you understand? We love to talk about minimums and maximums, and in fact, there's a lot of money to be made in if you can answer these questions, right? If you think about it, and when we get later in this chapter, we'll learn some techniques, what we call optimization, how to find these minimums and maximums if they exist. Now, other questions that we might care to ask is, okay, is the graph increasing or decreasing over some interval? Right? So, for example, if you would look at this random blue curve that I've drawn here, I think that you would agree with me that this, again, we have to be reading, you and I have to be looking at this graph the same. We have to be looking at it from the left to the right, right? From left to right. So we would say that it appears that this graph is increasing all the way till we get to some particular value. We don't, so it's increasing, right? The entirety of this interval all the way till we get to some generic x value that I have no idea what it is. Then it kind of stops increasing. And then after that x value, it's the graph starts to decrease, right? So I might like to know the interval where something's increasing or decreasing, or I might like to know when where is it constant. And let's do a little bit better than that, right? Like if you tell me, I'm going to clear this board here. If you tell me that something is increasing, right? If you tell me, I'll just draw something here. If you tell me that something is increasing, a population's increasing, a stock is increasing, a endemic disease of the rate of infection is increasing. If you tell me something is increasing, that doesn't quite give me a lot of information, right? Do you see what I mean? Like the following curve that I just drew is increasing, but so is this curve, right? This curve is also increasing. So another question that we're going to ask is, well, what's the rate of change of the rate of change? In other words, I keep drawing these two curves when I really just want one, but I guess it's helping serve the example. Let's go back to this original curve here. So in other words, if I ask you what's the rate of change of the rate of change, now that's an interesting question, right? Because let's take a look at what the slope might look like at this point right here. All right, and my apologies, I can't draw very well. And then let's compare it to what the slope looks like at another point. So do you see how, you see how the curve itself, or the slope itself, is increasing, right? See how m is your slope, right? Do you see how m is changing, right? Like, I don't know, if you like to walk up mountains, you like to backpack. I just let you and I agree that when you get to this point here, the rate of ascent is pretty steep, right? It's going to take a little bit more work for you to continue your backpacking. So all of these are great questions, right? Mins, maxes, increasing, decreasing, rates of change of the rates of change. All of these are the types of questions that we want to be able to consider. Now, we need to start with some definitions. So let's start with the definition of what do we actually mean by a maximum value on a function. Well, notice that I'm going to read it to you, but I'll try to do it in other words. It says, so first off, let f be defined on an interval I that contains C. Now, it is helpful if you take your time with these definitions, right? Like at some point in time, if you got a lot of math in front of you, you got to stop giving these, glossing over, giving these cursory looks to the theorems and the definitions, because if you really want to get good at this stuff, sometimes we got to dig in, and when you dig in, you'll find that really it's not that bad. So let f be defined on an interval containing C. Now, I'm going to just draw some random function. Now, I don't care about this function being defined from negative infinity to positive infinity. When they say on some interval I, we could think about that as, okay, from this x value to, say, this x value. Now, I can't read that. That looks like it's like -2 to +3. If that's not the case, don't laugh at me. Don't hurt my feelings. But look, what they're saying is, as long as the function from -2 to +3, as long as every point is defined in that function, right? We don't have any jumps, we don't have any holes, no vertical asymptotes, none of those things. Okay, then, and then we also say that it containing some value we're going to call C. All right, so some value that we're going to call C. So in other words, when this C is just some x value that is of importance to us, right? C is just an x value. It's just an x value, but it's important enough to call it C. Ready? Now let's get to the first part. It says f of C is the minimum on the function I when, ready? So let's just say that right here, here's C. Okay, so when do we get to say that this is a minimum, right? When do we get to say that f of C is a min, it's a minimum value? Well, we get to say it is a minimum on the function, a minimum of f on that interval when the following conditions apply. That f of C is less than or equal to f of x for all other x in that interval. Right? So do you understand that what I'm saying is, look, if you're standing here at C, right? If you're standing right here, you're here at C. If you were to walk to the right or to the left, let's look at it like you're on the graph here. So if you're standing right here at C, if you were to deviate slightly to the right or slightly to the left, you would be at a y value that is greater than you are if you would have just stood still. Does that make sense? I think that makes sense. So f of C is less than or equal to all other f of x. For, it's less than or equal to f of x for all other x values in that same interval. So there's no other values from -2 to +3 where the y value would be less than if you just would have stood still at the point C. So okay, so I hope that I won't go through. I could go through the exact same explanation for what it means to say a maximum, but I think we pretty much got the gist. Let's now just establish some vocabulary. So the vocabulary that we're going to use, and I just, you don't have to write it, but just listen to me for a second. There's different types of minimums and maximums that we're interested in, right? Like if you kind of graphed your salary over your lifetime, right? So let's say, I don't know, at some point in time, forget about these tick marks, right? So let's say your salary looks something like this, right? I don't know. In other words, at some point in time, you start working, right? Prior to that, you're not working, like my two boys are not producing any income, but at some point in time, you start working. And then notice that over time, like let's say right here. Now, I don't know what age you are. Hopefully you weren't 4 years old or 3 years old. But whatever age you are at that point right there, you were making good money compared to what you were making before. Am I correct? So now that's a type of maximum. But let's also take a look at whatever age value that you were at this next point. So we'll call this point P. We'll call this point Q. Now, both of those are maximums, but we need to qualify that, right? So we would say that point P, in this case, is the absolute maximum. In other words, at whatever age you were when you were making your salary at point P, that was the absolute most amount of money that you made in your lifetime. Agreed? Now, but point Q can also be thought of as a maximum, but we would qualify that by saying it's a relative maximum. In other words, relative to your surroundings, right? If you took a step to the right or step to the left, you would be making less money. Maybe that doesn't show up very well. So let's make sure you understand that dips. So if you walked slightly to the right or slightly to the left, you would be making less money than you were at point Q, right? So that's the idea. So we have relative mins, relative maxes, absolute mins, absolute maxes. So, all right. Now, just to that is the language that I'm going to use in this section. If you maybe don't like me, so maybe you go and find another video, which is perfectly fine. You may hear them say, instead of absolute maximum, they might say global maximum or global minimum. Okay, so now let's continue with our lesson. So we have a few definitions at hand, and we're going to jump in and start talking about relative extrema. Okay, so relative extrema henceforth means minimums or maximums, and they can be relative mins or maxes or absolute mins and maxes. Does not matter. We're just saying relative extrema. Ready? That you should be thinking, if you hear relative extrema, just start thinking, hey, we're talking about mins and maxes. Ready? Okay, so let's if we take a look at the graph at the bottom here. Now, this is the graph of y is equal to x squared plus 1, okay? That's the function, x squared plus 1. Now, notice part A versus portion A versus portion B. We have two different ways of defining the domain. So let's start with part A. So part A says that the interval that we care about is from -1 to +2, including -1 and +2. Whereas part B, we're looking at the interval from -1 to +2, but in this case, we can get as close as you want to 2, close as you want to -1, but we can't actually reach -1 or +2. All right, and now the question that you should have is, and the question that we're going to try to answer is, how do these slight differences in conditions, how do they determine whether you have relative extrema? Okay, so let's go ahead and start with part A, and then I'll come back to the definition after we've established some things. So I'm going to go ahead and we're going to start with part A, so I'll put an A here, and I'm going to go ahead and put a bracket here at -1, and I'm going to put a bracket here at +2, and that tells me, yes, that you actually can reach those points. Now what I want you to do is I want you to look at the graph, and I'm going to kind of try my best to trace. So that's the graph from -1 to +2, and now let me pose a question to you. Ready? Is there a minimum value, right? A minimum value. Is there a maximum value in that interval? Let's start with the maximum. So for sure, at the point 25 is the maximum value, right? Now, what about the minimum value? Well, don't you agree with me that this little blue dot is the minimum that y ever, the value of y that it ever takes under that, through that interval, right? It's not the point -1, 2. It's definitely going to be at the point 0, 1. So do you have a minimum? Yes. Do you have a maximum? Yes. Okay, so let's kind of put that in our pocket. So when your interval is defined from -1 to +2, including -1 and +2, okay, we have a minimum and we have a maximum. Now let's Let me erase these brackets, and let me put parentheses, and we're going to look at part B really quickly, okay? Stop being in a rush. You're okay. All right, but life is okay. Let's look at part B. All right, so now we're going from -1 to +2. We don't actually get there. We can just get as close as we want. All right, my question is the same. Is there a min? Is there a max under that new interval? Let's start with the min. Well, the minimum's the same, right? For sure, the blue dot is still the minimum value, which is 0, 1. Is there a maximum? I know what you're thinking. You're thinking, yeah, there's still a maximum. It's right here. Right where? Hold on for a second. The definition, right? Let's go back just a page. The definition of maximum said that f of c is a maximum of the function on I when, here we go, when f of c is greater than all other f of x. Right? So the definition of that maximum said when f of c is greater than or equal to f of x for all other x. Now, some of you already know where I'm going with this. Look, I know you can't get to 2, but if you get to 1.9, let's say that'll put you here. Can I get any higher on the graph? Yeah, I can. I'll just go to 1.99, right? And that'll get me a little bit higher. And 1.999 will get me a little bit higher. Do you see how this game doesn't end? Do you see how you'll never get to your maximum value because you can always keep getting closer and closer to 2? So let's answer the question. Is there a max? No. There's no maximum value on this function. There was a minimum, but there was no maximum. Let's go to this definition of relative extrema, and let's hope that we can start to piece all this together. Okay? So I'm going to free myself up for I'm going to give myself some space. And let's see if we can try to generalize some of these little observations that we've been doing, or that we've been noting, okay? So if there is an open interval, I'm going to read, and then I'll do in other words, right? So if there is an open interval containing C on which f of C is a maximum, then f of C is called the relative max of f. Or you can say that f has a relative maximum at some point. In other words, there's a difference between me asking you, what was the most money you ever made in your life? Right? If I asked, if you were plotting money here and age here, if I asked, what's the most money you ever made in your life? That would be asking for a Y value. Right? If I asked, at what age were you making the most money you ever made in your life? That would be an X value, right? So there's a subtle difference in the way we word the questions, but a max, a relative max, or a relative min, it just I think you understand the overall gist. But a maximum is a point, right? You would give me an age and a salary if we were back to that scenario. But so a maximum value is an XY point. Just keep that in mind. But if all you care about is just the Y value, then you could simply phrase it as what was the salary, the most money that you ever made in your life. Okay. So what that observation, the kind of the takeaway, is that if you have the first example, the part A, what do we have? Well, one, we had a closed system. right? If you rewind just a second, you can see that we were defined from -1 to +2. That's a closed system. We start at A and we stop at B. The other thing that we had was that your function was continuous. All right, I could draw without ever lifting my my stylus, if you will. Now, we're going to make a claim that if you have a closed system and your function is continuous, we're going to say that you are going to be guaranteed to have a min and a max. Right? This is a guarantee. This is a stamp that you are gonna, if you meet those two conditions over some interval I, you're gonna be guaranteed a minimum and a maximum. Now, in part B, well, we didn't have a closed system, right? We had an open system. In other words, we went from -1 to +2, never actually reaching either of those extremes. But of course, the function was still continuous. So we're gonna make a claim that if you meet the qualifications of a closed system and a continuous function over an interval, you're going to be guaranteed a minimum and a maximum. If you don't meet those two conditions, all we get to say is that you're just not guaranteed a minimum and a maximum. Okay, so we got to be careful in mathematics with the converse of statements and the way we treat these statements. But it's just, we would be saying that, well, you might have a minimum, you might have a maximum, you might have both, but you're not guaranteed, right? So let's go ahead and continue, and let's jump into some problems. So how do we go through and start to think about minimums, maximums, and how do derivatives and the study of calculus play a role? So the definition that I just gave you, that guarantee, is where if f is continuous, if f is on a closed system and continuous, this is what we call the extreme value theorem. Now, I thought that I actually had the theorem on this on the slide here, but I don't, and I'm not going to try to reproduce it off the top of my head, but it does. You can go with my claims. It's if f is continuous on a closed interval a to b, then f has both a min and a max. It's going to be something like that, right? Now the proof of that extreme value theorem is actually beyond the scope of this class, but let's now get back to my question of how do derivatives play a role. So let's play for just a second. So what I have is I have three functions, and off to the right I have the three graphs of each function. And let's read the question. It says, find the value of the derivative at the relative extremum, right? So here's the relative extreme. I don't like that. Let's change that color. So here's a relative extrema, here's a relative extrema, here's a relative extrema, here's a relative. So each of these graphs has relative extrema. We want to talk about the derivatives, the value of the derivatives. So if you will allow me, okay, please just let me write the derivative for each of these without walking through it. That was the point of the previous chapter, was how to take the derivative. So if you would like, you can always pause the video if need be and go back through and or pause the video and see if you can produce these derivatives on your own. I'll leave that up to you. But as of right now, if you allow me, just let me go ahead and give you the derivatives, okay? Okay. So let's start. So let's, so you'll have to, if you're like me, if a lot of times I can't, if I get started on a problem, I can't turn it off, right? So please don't listen to me talk as you're trying to find the derivative, right? Pause it. Take, just let's actually, if you really want to take the derivative and see if you can get to where I'm at right now. But our question was, so in this case, we're given the graph, and we can see that there's a relative max at the point, right, at the point 3, 2. So the x value is 3, the y value is 2. Now, what we want to do is evaluate the derivative at that point. Does that make sense to you? So in other words, so x is 3. So we want to see what this derivative looks like when you plug in a 3. Okay, so a derivative is useful but it is not a slope. A derivative is a function, right? A derivative is a function. It will give you a slope, right? It will give you a slope, but you have to give it something. You have to give it, in this case, an x value. So if I plug 3 into my derivative, I end up with 9 times 9 minus 9, or 9 times 0, over, well, whatever the heck 3 to the power 4 is, but that leaves me with 0. Okay, so that's interesting. So it appears that slopes are 0, right, at relative extrema. Okay, well, let's see if we can continue here. So what about the derivative? And so let's take a look at the absolute value of x. By the way, if you've never taken the derivative of the absolute value of x, it's just, if you don't mind, bear with me here. I've produced it, just quickly in its entirety here. You would have to pause the video to walk through. You have to use the limiting definition, but I'm not going to go through that setup here. I'm just going to go back and we're going to assume that since I have red pens that you will accept that I'm right, right? Okay, so now let's look at the graph. That was a joke, by the way. You should never accept just because somebody's a teacher should accept that they know what the heck they're talking about. But what we have in this case is when x equals 0, there's definitely a relative minimum. Now, but our question is, well, what does the derivative look like? So you would be asking, what does f prime of 0 look like? Well, you can see that if you plug in 0, well, you got a problem, and that problem is not going to be resolved. What we're going to be able to say is that, I'll generalize this in just a second, but what we're going to make the statement that we're going to make is that f prime of 0 does not exist. Okay, there's no way around this. Now, I can generalize this to say that at sharp corners, derivatives do not exist. Now, it's very loose and that's very sloppy, but at sharp corners, derivatives do not exist. I will just leave you with that. But all we're doing right now is collecting information. We're going to continue. We're just collecting information about what the derivatives look like at extrema. So last, let's look at the derivative of cosine of x. So I'm looking at my graph here of sine, and it looks like when x is pi over 2, right here, so when x is pi over 2, you got a max. When x is 3 pi over 2, you have a min. And now what we care to ask is, well, what does f prime of pi over 2 look like? What does f prime of 3 pi over 2 look like? What do the derivatives look like? Well, if you have your, if you know your unit circle, or if you have access to your unit circle, you could look it up. But look, cosine of pi over 2, right? Cosine of pi over 2 is 0. Cosine of 3 pi over 2 is 0. Okay, so interesting, right? So from those, I realize that's only 3 examples, but from those 3 examples, it appears that relative mins and maxes are showing up when the derivative is equal to 0 or when the derivative does not exist. Okay. So, in fact, let's actually start to generalize that into a statement here. So, let's start with the definition of a critical number, and then we'll get to the theorem. Ready? So it says, let f be defined at some point C. Again, stop taking these definitions for granted. All it means is there's at some point C, and if you plug it in, you will get a y value. Okay, so it's defined at C. It says if f prime of C equals 0. Okay, well, hold on for a second. F prime of C, that would mean that the slope at the point C is 0. Or, okay, well, so let's say if f prime of C equals 0, or if f is not differentiable at the point C, then C is a critical number of f. All right, so in other words, this is when your slope equals 0. And of course, we've already talked about when derivatives do not exist. So let's just try to capture that. Let's try to capture that statement in our own words here. So critical numbers occur when either the derivative is equal to 0 or the derivative does not exist. Are you with me? So that's what we call critical numbers. On that previous page where the derivatives were 0 and the derivatives do not exist, as long as that x value is defined on the real function, that's what we call a critical number. Okay, so now what does that do for us? So why take the time to learn this vocabulary? Well, so the theorem, and I'm gonna shrink this in just a second, so bear with me. It says, the theorem says if your function has a, ready? Let me make sure you're following me. If your function has a relative min or a relative max at the point C, then C is a critical number of the function. Okay, so I need you, right? So you have a lot of math in front of you. I need you to start to understand some things here. This theorem is an if-then statement. Right? Notice the setup. It's if there is a min or max. Right? If the function has a relative min or max. So if there's a minimum or a maximum at some point C, then C is a critical number. All right, don't switch your if-then statements. Don't switch your consequence and your antecedents. Right, your if-then statements are conditional statements. They're not biconditional statements. You don't get to switch them around. If you have a relative min or max at a point C, then then C is a critical number. That's the takeaway. So now that's actually good news for us. So let's see if I can. Let me get rid of this for right now. Bear with me here as I learn my technology. I'm going to copy it so I can get rid of it. I'll bring it back if I need it. So actually, all of this work, all of this time with these definitions, because this is actually really good news. If you want to find mins and maxes, then the game is going to be as follows. You're going to take a derivative, and you're going to figure out where the derivative is equal to 0 or where the derivative does not exist. And then we're going to use that information, as well as, in this case, the starting point and the stopping point. We're going to use these little pieces of information to find the minimums and the maximums. Ready? No more theory. Let's jump in. Let's get started. So example 2, it says find the extrema. Find the extrema of the function 3x to the power 4 minus 4x cubed on the following interval. Okay. So in this case, I'm going to be giving you derivatives. I'm not going to be showing you how to take derivatives anymore, unless they are tricky enough that I want to make comments about them. But right now, I'm going to assume that you know how to take the derivatives that I'm about to take. So the derivative is 12x cubed minus 12x squared. All right. So how about I give you some steps, right? Like a recipe. So step 1 is going to be find f prime. Got it? All right. So step 2, I'll write it. So step 2 in this case is going to be for you to find the critical numbers. So find where f prime of x is equal to 0 or does not exist, right? That's our definition of a critical number. So that's what we're going to do in step 2. All right, so let's start with when the derivative is equal to 0. So let me rewrite. So I have f prime of x is equal to 12x cubed minus 12x squared. All right, so I'm going to set this derivative equal to 0. And I'm going to factor this, right? Listen, you've trained all your life with all these factoring techniques. Because of this scenario, well, let me say, because where we're going right now, it's a whole lot easier to find out what x values make this equation equal 0 if it's in factored form. So I'm going to factor out a 12x squared. Now I would be left with an x minus 1, right? So you went from like you can think of it as you're going from sums or differences to products. And the beautiful thing about a product, right? So we have two parts, two factors. If I can make either one of those equal 0, then by definition the other is equal to 0. So let's figure out what would make our first part equal 0 and what would make the second part equal 0. All right, well, the only way you're going to make 12x squared equal 0 is if you pick x as 0. And the only way you're going to make x minus 1 equal 0 is if you pick x as positive 1. Does that make sense to you? So now look, if I plug 0 in for x, I don't care what I don't care what 0 minus 1 is, because that's anything times 0 is going to 0 out. So that's why you spend all that time training to factor, is so you can turn sums and differences into products, and you can use these, what we call these zero product principles. All right, so let's start. So we're still at step 2, and what are we doing right now? We are collecting critical numbers. So there's definitely critical numbers when x is equal to 0 and when x is equal to positive 1. Now, that's where the derivative is equal to 0. Let's go back. Let's go back to the derivative. Is it possible for that derivative to not exist? Right? We're at this other part here. Well, no, because for your derivative to not exist, that would mean that you would be trying to divide by 0 or trying to take the square root of a negative number. Don't you agree with me that there's no fractions here? You don't have to worry about dividing by 0. There's no, and you know, there's no radicals. We don't have to worry about taking the square roots or even roots of negative numbers. So, in other words, the derivative equals 0 at 0 and 1, but the derivative never not exists, right? It exists throughout the entirety of its domain. So that's step 2, was to find these critical numbers. Now, step 3, okay, ready? Is we're going to evaluate the critical numbers. So let me write it. So I'll do it just this one time. So we're going to evaluate, I'm just going to say plug in. We're going to plug critical numbers into f of x. Now, if you want, you are going to end up plugging in if you kind of follow me up here, you are going to end up plugging in the bounds, or the negative 1 and the positive 2 in for f as well. But I'll write that in a fourth step. So plug the critical numbers into the original function. Please don't plug in your critical numbers into your, I'm going to plug in the 0 and I'm going to plug in the 1. But don't plug it into your derivative, right? If you want to know the mins or maxes, you're asking about where it is on the y-axis. So if I plug 0 in for the original function, right, that would be 3 times, I'm going to write this only this one time, 3 times 0 to the power of 4 minus 4 times 0 to the power of 3. That means f of 0 is equal to 0. F of 1 is equal to negative 1. Okay, as always, double check, make sure my arithmetic is correct. So step 4, and you can make this into just 3 steps if you want, but step 4 is going to be to plug your points or your bounds. How do I want to say this? Your endpoints. Let's say plug endpoints into f of x. All right, so I'm using the same original function, not the derivative, same original function. But let's go ahead and establish, so the endpoints, so it says on the interval from -1 to 2, that means when x starts at -1 and x stops at +2. So we want to plug in the endpoints, -1, +2. And let's go ahead and say what pops out. So if you plug in -1, you get out a 7. And if you plug in a +2, you get out a 16. Okay. Now, are you ready? Are you listening? Can you put your phone away? Put your controller down for just a second. Come back to me. Come back to me for just a second because we're almost done. This last step is where you're going to figure out your mins and your maxes. So ready? Let me get a different color here. So which one of these 4 y values, which one is which one is the largest? Well, that's where your max is. Which one's the smallest? Well, that's where your minimum is. Okay? So step 5, that's that find the min max. Ready? Let's do it. So there is a minimum. Let's start with the minimum. There's a minimum at the point. So let's see. -1 is the smallest y value, right? -1 is smaller than 0. It's smaller than 7. It's smaller than 16. So there's a minimum at 1, -1, right? See how I'm just taking when x is 1, y is -1. All right, now let's find the maximum, because you're guaranteed to have, in a closed interval, you're guaranteed a min and a max. All right, so that 16 is the largest value out of all 4 of those. So that means when x is 2, y is 16, that is your maximum. Do you see what we just did? So I'm going to conclude this video, and I'm going to do a part B where we're just going to continue to practice this skill set. But all I'm going to do is more of the same procedure, right? You're going to see me do steps 1, 2, 3, 4, 5 over and over again, just with some different variations. And I will see you soon.